Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to discuss about module 14, which explains dynamic programming algorithm design technique. Now, here in this module, we are going to discuss about two topics. First one is principle of optimality, and second one is optimal binary search trees. So here, in this session, we are going to discuss about principle of optimality. So which is a very smallest topic, which explains about a small principle which we use in dynamic programming. Right. Now, let us see. This principle of optimality was introduced by the scientist Richard Wellman, who is a prominent American mathematician and computer scientist. So it was introduced by the scientist. And the principle of optimality is a fundamental concept in the field of dynamic programming and optimization. Right. Now, the principle is a key idea. This principle is a key idea used to solve optimization problems efficiently by breaking them into smaller and overlapping subproblems. Right. So here the principle, this principle is a key idea behind breaking the larger problems into smaller problems and overlapping subproblems. So the principle of optimality guides the design of efficient algorithms for solving complex optimization problems by breaking them into simpler and overlapping subproblems and reusing those optimal solutions to these subproblems. Right. Now, first of all, what is the principle of optimality? How it can be stated? It states that an optimal sequence of decisions or choices, each subsequence must also be an optimal. So, if you have an optimal sequence of decisions or choices in solving your problem, each subsequence must also be optimal. Every subsequence, thus if I take one sequence, for that sequence, every subsequence should also become optimal. So it is not possible to derive optimal solution using dynamic programming if the problem doesn't possess the principle of optimality. So if the problem is not possessing the principle of optimality, it is not possible to derive the optimal solution for that problem. Right. Now, for better understanding of this principle of optimality, we are going to see an example. Let us see the example. Consider the problem of finding the shortest path in a graph from a starting node to an ending node. So always the shortest path problem satisfies the principle of optimality. Now let us see how it is satisfying the principle of optimality. Now here we are taking a sequential path which starts at a node A and which ends at a node B. So I want to find the shortest path between these two nodes. For finding the shortest path between two nodes, we need to travel via some other nodes such as x1, x2, so on, xn, via other nodes such as x1, x2, so on, xn. So if this path A to B, that is the path what we consider, becomes an optimal path if the subpath xi to xj must also be the optimal, must also be the shortest. That is, if I consider a subpath x2 to x3, this should be optimal. If I consider a path from x2 to x4, this should also be optimal. That is, it should have the minimum cost. Right. So in a better way you can understand. So where principle of optimality holds and where it not holds, for understanding that, here we are taking one more example. So here let us see, I have given two graphs. So in the first graph there is a path from B to E, there is an edge from B to E, but in the second graph there is no edge from B to E. Now here let us see, corresponding to the first path, I am going to take the shortest path from A to C. Now, what is the shortest path from A to C? Since there is no direct edge from A to C, whether I need to travel via B or I need to travel via E and D. So here there are two paths are there. One path is A to B and B to C. Another path is A to E, E to D, and D to C. Right. But by seeing each edge is having one unit of weight. So in this case, this is having 1 unit and this is having 1 unit. Total cost is 2. This is having 1 unit. This is having 1 unit, and this is having 1 unit. Total cost is 3. Since this is having minimum cost, we can say that this is the shortest path. Right. So now, if I see B to C, I am taking a subpath. I am taking a subpath of this A to C. That subpath is B to C, let us say. Now, what is the shortest path of B to C? So here I can travel directly from B to C, or I can travel in this way to B to C. That is B to E, E to D, D to C. Right. So these two ways are there to travel from B to C. Right, without considering this A. These two ways started. Out of these two ways, this is the shortest one. This is the shortest one. That is, the subpath is also shortest. Here, this total path is shortest, and this subpath is also shortest. That's why we can say that it is satisfying the principle of optimality, and whatever the path we calculated is the shortest path. But if I am taking the longest path problem, let us see. In the figure B, I am going to take the path from A to D. Right. What are the paths from A to D? A to E, E to D. This is one path, and another longest path is another path is A to B, B to C, C to D. Now, out of these two, which is the longest path? Obviously, this is the longest path. If I am considering each edge is of 1 unit of distance, right? So now, in this longest path, if I am taking a subpath B to C, if I am taking a subpath B to C, is this subpath B to C is a longest path from B to C? I can travel from B to C via A, E, D, C. That is, this is the longest path from B to C. But this is not the longest path, right? So that's why, is it becomes an optimal? No, since this is not satisfying the principle of optimality, right? So always the shortest path problem satisfies the principle of optimality, but the longest path problem doesn't satisfy the principle of optimality. So longest path problem cannot be solved by using this dynamic programming, but shortest path problem can be solved by using this dynamic programming. So I hope that you all understood this principle of optimality, the concept of principle of optimality. Now, try to understand by considering some more examples. Thank you for listening. Thank you.